Welcome back. I would like to go further in the lecture on gaming simulation by showing you two examples. ProRail is the Dutch railway infrastructure manager. In the Netherlands, we have a separation between the company that operates the trains, there are actually multiple companies, and the public agency that operates the rails and does the traffic control. And there we have a long-running project trying to reduce the uncertainty in their decision-making on changing the operations. And this is a 4-year contract that we have working on some very interesting projects. We use both computer-based and analog games here. And that depends upon the phase in the decision-making and the complexity of the question at that moment. Now, if you think about how innovation in railways is usually done, it's usually fairly top-down. There are engineers, specialists that really know how the system works, and they test their potential solutions in computer simulations, and then they push it to the operations. The operations should do what they designed. But will it work in practice? We know in many railway systems that robustness and resilience is already under pressure. Railways are great if they work. If they don't work, then it's usually a mess, and that's true in many countries. We also know that the engineering has many assumptions about how the operations actually work. But a nice phrase here is that the difference between theory and practice only exists in practice. So the operators know what the differences are, but the engineers are usually not aware. But if you start talking to the operations, that usually doesn't help. Why? Because it's very hard for them to reflect upon something that is not their daily reality. They have very effective mental models that help them in doing their daily work. But if you start doing it with them in a game, then actually you get a lot better feedback. So the challenge that we have here is we want to have 100% extra trains in 2020. At least that used to be the plans. By now, it's a bit adjusted. And the goal was to have 50% extra trains on a regional, in the western side of the country, by 2012. Starting on the major corridors, you could see Amsterdam maybe, which is at the right, at the western part of the Netherlands, and then south to Eindhoven, a city almost to the Belgian border if you look at it from a bit larger perspective. The goal was to get to an untimetabled traffic, like a metro system. With a metro, you don't know when the actual metro comes. You just go to the station and you pick the first train. Now, that would be great to do with the train system as well. However, to do so in the traditional way, in the old way, it would require a lot of money. And that is by going into new infrastructures, building new rails, etc. And that money simply wasn't there. But about 10% of that budget was available. So can we do this smarter? The project, every 10 minutes a train, ETMET in Dutch, was a real-world test done in September 2010 between Amsterdam and Eindhoven, as I said, in what we call a 662 pattern, which means 6 long-haul trains, intercities, 6 short-haul trains or commuter trains, and 2 cargo trains. The preparations started in the spring of 2010, and the question was, what if a disruption occurs? How can we handle this? And there were 2 types, the traditional type and a new type, defined by staff experts. Now, the question to us was, can you test this with the operators, whether this will work? I'm now going to show you a movie where you see what we actually did. NS is the major railway train operator, and together with ProRail and us as facilitators, we held this gaming session. What we did was having an analog simulator where you see some digital simulators here in the movie as well, which were used as a reference. If everything would go well, then the digital simulators would be the truth. However, of course, we were going to introduce a major disruption. And you can see here some people that are pushing scour sponges. Very simple models, but with real numbers to it, and they represent trains. They run over an infrastructure map, which is the real infrastructure map. You also recognize that there are all kinds of things plugged into the scour sponges. And these represent train drivers and heads of cabin. This manual simulator, as you could call it, was controlled by these people sitting in control rooms and being connected by two-way radios and video streams. Together, there were 3 of these control rooms, each with their own particular responsibility. Together, they needed to solve, and we could compare the 2 different scenarios in the morning and the afternoon. So what did we do here? We modeled reality. We modeled trains, for instance, by scour sponges. Combinations of wagons of a particular type were possible by just connecting different scour sponges on a piece of a wood stick. And everyone had its associated capacity as if in the real life. There's 1 train driver and 1 head of cabin required, and those were flags with the real numbers. We also had route setting, again on a real map, and a timetable with real numbers, even though it was the future timetable with 50% more trains. So the data sheets were all as realistic as possible. Some were even real, taken directly from the operations today. And then trying to mimic the workplace of the particular operators by having video distributions instead of their regular computer systems. Telephone, real phone, and intercom were replaced by portaphones, which worked very well. Now you can think, okay, if it's so simple to simulate something, what type of models do I actually need to use? I often make a distinction between what we call an iconic representation, and that is needed for all the relevant elements, all the elements that you need to take seriously. And if you see this icon anywhere on an airport, you know where to go to the train. So this is fairly iconic, fairly recognizable. Some things, however, you need to make as if real, and those are the crucial elements that people really need to pay attention to. But you also want to sketch a bit of an environment. And there you can use playful elements. So here I have 3 pictures of a train, and they mean something entirely different, which for a computer simulation doesn't make sense. But for a gaming simulation, where we have people, it makes a lot of sense to do so. A second example. This is called SprintCity. It's about the relation between urban development and the development of the transport system. It's been developed for an agency called the Delft-X Metropole Foundation. And it's about connecting the urban inner city areas through metro-like trains again. And then trying to perceive the urban development of these inner city areas around the stations as if they were one connected city, really a metropole. We built a computer-based game here to be played with domain specialists of all kinds of backgrounds. So it could be people that are politically responsible, people that have some engineering responsibility, and we could give them fictitious or even real roles in this game. So you see some pictures here where you see a particular city. This is a map. Around each station we had 1,500 meters circles, and of those circles, of those maps, we got a lot of information, which is publicly available nowadays. And with this, we built a computer game, and you can see here at the bottom that we have groups playing that. What you would do is to define your own ideal station environment with different types of buildings, different types of living, offices, etc., etc. And then you need to build that over a period of time, a long period of time. And we have a model-based evaluation of the balance between all these inner city centers that are connected. If you build offices in one place, it's not very useful to build the same offices in the other place as well. However, if you only build houses in one place and offices in another, you're going to overload the transportation system. So there are all kinds of constraints, and we had all kinds of equations, however, behind a purely qualitative interface to make sure that every actor even if he's not from an engineering type of logic, can play this particular game. The learning outcomes are that the complexity and the dependency in urban development between transportation and the success of cities is very important. And this we achieved. So where's this going? You saw an analog game using real data. You saw a digital game. I believe that gaming, computer simulation, and big data, so trying to capture the entire world by all the digital traces that we leave behind, this is going to integrate. And this will lead to multi-scale modeling and data-driven gaming more and more. However, we need a lot of research to get there and to make those tools ready. Meanwhile, in the visualization and interactivity computing domain, you see that the technology of using 4K projectors and extremely large data sets becomes useful for gaming users, for real-time interactive use. There's a third trend, and that is that decision-making in public administration tends to become more evidence-based. The politicians know that they need the knowledge of how the system actually works, same with the managers, to make good decisions. And this is where we'll use joint fact-finding. So together, this will integrate the operations in strategic decisions. So you could visualize this as if you have gaming simulation, this builds on top of advances in visualization and interactivity, as well as in analog platforms. Those are fed again by big data, distributed simulation, as well as cognitive task analysis to actually understand what the operators do. This leads to all kinds of interesting research questions. You can research culture, cognition, human factors research, robustness and resilience, second-order effects. All these types of things are possible to study if you integrate this domain. And this will lead to better holistic decision support, better design of innovations, and all kinds of changes in decision processes, and maybe even leading to a better sustainability of systems if we use a systems of systems research approach. Now, to make a long story short, the design of infrastructures is a multi-actor problem. We need many people to actually design these complex systems. That requires methods that involve these people in the decision-making, and not just the politicians or the high-level decision-makers, but also the operators and the engineers. Gaming simulation is one way to make a contribution here. I thank you for your attention. If you have any questions, you're very welcome to post them on our discussion forum.